Check it out now, y'all.
NanoHub U, online instruction.
Hi again. We're back, and we're going to discuss in this lecture something called the Boltzmann factor, and we're going to derive that Boltzmann factor by considering how distinguishable particles are distributed in quantized energy states. So we're going to take a lot of the ideas that we've discussed in the previous 3 or 4 lectures, and we're going to systematically apply them to this quantized energy spectrum. In the process, we're going to get out our screwdrivers and wrenches, and we're going to try to understand how all these probabilities work in detail. I think it's the only way that you can really understand what the theory of distributions in quantized energy states entails. I think you just have to work through some of these simple examples in great detail, and in the process, you should be able to derive an understanding in your own mind about what actually is going on. So the approach I'm following is not so much derive these general equations, which you then have to learn how to apply. I'm more interested in trying to teach you how those equations have been developed by picking specific problems that are simple enough that we can work out in the course of 20 or 25 minutes. So I hope this approach increases your understanding of these problems, which are inherently simple enough to state, but when you get into the details of the mathematics, it can get complicated. So there's basically 2 central themes to this lecture, and I'd just like to quickly review what those themes are. What we're going to try and do is we're going to try and apply these probability arguments that we discussed about flipping coins or pulling marbles out of the hat. Right? We're going to try to apply that to a physical system. And the physical system that we're going to focus on is a system that specifically has quantized energy levels. So we're imagining a confined region of space. We're imagining taking distinguishable particles. We're doing distinguishable particles first because it's a little bit easier to sort through things. Right? We're taking these distinguishable particles, we're dropping them into a system, and we're going to, for the sake of argument, we're going to say that the energy levels in this particular quantum system occur at integer values of some parameter epsilon, right? So this is the quantized ladder of energy states that are available, and we're just going to ask how these particles are distributed in these energy states, and in particular, we want to know what the eventually we'll ask what's the temperature of this system, right? Because the temperature of this system is then going to determine how these particles are distributed, right? And we're going to work out the details of a couple of these problems and show you all the steps that you need to demonstrate in order to show that you really understand what's going on. Some of you may recognize that these different energy levels could be degenerate. They could have multiplicities associated with them. That we're not going to discuss in this lecture. We're going to basically assume, for the moment at least, that all these energy levels are singly degenerate, which basically means there's not multiple quantum numbers that are required to store particles in these energy levels. Because the particles are distinguishable, that means we can put more than one particle in an energy, or more than 2 particles in an energy level. So don't get confused about our discussion of fermions that we conducted back towards the end of the section on the hydrogen atom. If these particles were fermions, they would be indistinguishable. They would have spin 1/2. And the maximum number of particles we could then put in a given energy level is 2. We are not discussing that problem yet. That'll come later on. So these are the constraints of our really simple system. We just want to think through it and show you what's involved based on all these concepts that we've discussed in the prior lectures. So if you like an overview, this slide provides an overview of what exactly we're going to discuss in this lecture. And we're going to attempt to answer three particular questions. We're going to ask, what is the probability of finding a particle at a given energy level? Right? We like to be able to calculate that. We like to ask the question, how many energy states are there in the system? And we want to count those states as a function of energy, so we'd like to solve that problem. And then we'd also like to ask the question, what's the occupation number? In other words, how many particles are there in a particular energy state? If we made measurements, many measurements of this quantum system, and measured the energy of each particle that we pulled out, we'd like to know how many particles on average would be in state 1, how many particles on average would be in state 2, and so on and so forth. Again, I emphasize these are distinguishable particles. We'll extend the discussion to indistinguishable particles later on. Okay? So, the key result that we're going to derive from this discussion is something called the Maxwell-Boltzmann Factor, which is not the same as the distribution function. And this Maxwell-Boltzmann Factor was mentioned briefly in lecture 6.05. It was kind of just written down because we needed the result. This lecture, we go much more into the detail that underlies this particular factor. To sort of constrain the discussion to a system that's manageable, I like to just define the system that we're going to discuss. The system is going to contain just 4 distinguishable particles. That just means that the distinguishable means that we can color each particle by a different, we can label each particle by a different color in principle. So we can keep track of where they're going when we confine them into this small region of space. We're also assuming, for the sake of simplicity, that the energy levels are equally spaced, and the spacing between energy levels is just given by this parameter epsilon. That's a constraint that can be easily relaxed. The problem is if you relax it, then the arithmetic just gets a little bit more complicated. And the other constraint that's part of this discussion is we're going to only allow a certain amount of energy to be distributed among these 4 particles. And for the sake of discussion, we're just going to pick 5. 5 units of energy are going to be pumped into this system. So the collective total energy that all 4 particles have must equal this quantity 5 epsilon. Okay? And what we're going to say is we're going to say that there are N1 particles with energy epsilon 1, there are N2 particles with energy epsilon 2, so on and so forth. So the small n's are going to describe how many particles there are with a particular energy, and n is going to be an integer number, right? In principle, n is going to range between 0 and 4 because it's possible that there are no particles with a particular energy E1, or it might be possible that there could be as many as 4 particles in one energy state, given the fact that that's not going to happen because the total energy is 5 epsilon, but in principle it could, right? So we have 2 fundamental constraints that can be written down. Right? These 2 constraints are that the total energy of the system has got to be equal to this 5 epsilon, and that just means that the average number of particles in the state R times the energy of that state epsilon R, when summed over the 4 particles, has to be 5 epsilon. The other constraint is that the total number of particles is constrained to be equal to 4, right? So it's important for you to understand these restrictions up front because they provide a manageable system that we can do a calculation in a finite amount of time. So in order to calculate these probabilities, what we have to do is we have to first identify all possible states that have a fixed energy of E total equal to 5 epsilon. And I don't think there's an easy way to do this. You just basically have to sit down and start trying different configurations of particles and different energy levels. And after a while, you start to get a sense of what's going on. And it turns out for this system, there are 6 possible configurations, right? And so this provides like a microscopic model of how the particles can be distributed in energy with this condition that E total has got to be equal to 5 epsilon. And to be consistent or to provide a notation, we just call each possible state a letter. So we've got state A, state B, state C, state D, state E, state F. 6 possible states. And I think it's pretty simple for you to realize that the total energy contained in each state has got to be equal to 5 epsilon. And that's actually how I generated these states, by just systematically considering where the particles have to go such that the total energy is 5 epsilon. So just, for instance, to discuss state A, it's possible that you have 1 particle in the 5th energy level, and the other 3 particles would then have to be down here at 0 energy. State B is derived from state A because it just says, well, you take 1 energy unit from this guy, which means this guy jumps from here down to here, so this is 4 epsilon. To make up the total of 5 energy units, I then have to promote one of these particles into the 1 epsilon energy level, right? And so on and so forth for the other configurations. So it's important for you to understand how this microscopic model was generated. And once you've got this microscopic model, and once you've identified these 6 states, then you can start to ask, how many different ways is it possible for me to get state A? How many different ways is it possible for me to get state B? So on and so forth for the other 6 states. And so to sort through that, I've made this slide, and we're going to use this n choose n expression that we've discussed last week. And so what I list is, I list the macrostates labeled A through F. I list the occupation of particles in each energy level. So let's focus on state A, 3 particles in 0 energy level, 1 particle in energy level 5. And then I ask, how many different ways is it possible to achieve this state? Well, the answer to that is, if you got 4 particles, right, and you just choose 1, right, and the one that you're choosing is the one that goes in this state 5 epsilon, what is the expression for 4 choose 1? And of course, you have to evaluate this expression here, where little n is equal to unity. And when you evaluate that, you find that there's only 4 different ways to achieve this particular macrostate A, right? So this 4 is now the degeneracy, or the weight of that particular state A, right? That's the weight of state A. You can do the same thing for state B, right? State B, if you look back at the previous slide, had 2 particles in the 0 energy level, 1 particle in the 1 energy level, 1 particle in the 4 energy level. So how many different ways can I arrange those particles to achieve state B? Well, there are 4 different ways to achieve 1 particle in state 4 epsilon, in the energy level 4 epsilon. So that's 4 choose 1. And then of the remaining 3 particles left, I have to choose one of those to put into the first energy level. So the degeneracy, or the multiplicity of state B, is 4 choose 1 times 3 choose 1, and that turns out to be equal to 12. So that's how I get the multiplicity of the microstate 12 for state B. I list the formulas that I use to generate the multiplicities for the other states. You can check my arithmetic and see that these multiplicities are in fact correct based on this very useful formula. So this is really helpful because what it allows you to do then is it allows you to sum up all the possible microstates of the system, and it turns out when you count up all these degeneracies, you've got 56 different ways to distribute these 4 distinguishable particles in these quantized energy levels such that they have a total energy of 5 epsilon, right? And once you know the total number of ways you can distribute those particles, then you can start to calculate probabilities that particles are in particular energy states. And I like to illustrate that in the next slide. So for instance, I can ask, what's the probability that a particle will have a certain energy? And I can answer that question now because I've already constructed this table. So let's focus on the 0 energy level state here, right? To begin with, I circle it in red, and I just want to ask, what's the probability if I pull a particle out of this system, what's the probability that that particle has 0 energy, okay? And I define that as to be P, where epsilon is equal to 0. Well, how do I calculate that? Well, I got to know the probability that a particular state occurs, and I got to know the fraction of particles that have that particular energy. And I have to multiply those two, and I have to sum over the states of the system. So the fraction of particles having 0 energy times the probability that that state will occur just means I've got 6 states that I have to sum over, and those 6 states are listed in this particular line, right? The probability that I get state A is 4 out of 56, so that's this probability. The fact that I've got 3 particles in the 0 energy level state means that 3 out of 4 times, if I pull a particle out of if I pull a particle that's in macrostate A, 3 out of 4 times, I will find that particle in the 0 energy state. So that just is the first possibility of these 6, and I have to add to that the probability that I find a particle in state B. Well, the probability that I find a particle in state B is 12 out of 56, so this is the probability. And since 2 of those 4 particles could be in the 0 energy state, if I grab a particle that's in the macrostate B, then I've got to multiply the probability times this factor 2 force, which just tells me the fraction of the particles that have 0 energy if I happen to sample a particle from the macrostate B. So I can work this out, right? And I've done it here. You can check my arithmetic, and what I find is that the probability that I get a particle in the state epsilon equal to 0, right, is 21 over 56. That means that if I, for instance, sampled on average this particular quantum system, if I sampled it 56 times, I pulled a particle out, I measured the energy of that particle, wrote it down, and throw the particle back in, right? 21 out of 56 times, I should get particles with 0 energy, okay? What's the probability that I would get a particle that has 1 unit of energy, so 1 epsilon? Well, I worked that out just to reinforce the concepts. I focus on this row or this column of this table, and I work out the number here. And what I find is that there's 15 out of 56 is the probability that I would have a particle with an energy of 1 epsilon. So if you can do 0 epsilon and 1 epsilon, then it's pretty easy to do the others. I won't go through the arithmetic, but I will list the final table, and the final table is here, right? So this table tells me the probabilities that I will find a particle with 0, 1, 2, 3, 4, or 5 units of energy. And once I know these probabilities, right? Once I know these probabilities, then I know everything there is. This is like the probability distribution function for the Maxwell-Boltzmann distribution, except now my energies are quantized, they're not continuous. And once I know these probabilities, I can start to answer all kinds of questions about the system. So for instance, I can ask, what's the average energy of a particle in that system? So if I did 100 measurements, pulled out a particle, measured its energy, right? I average those 100 measurements of energy. What's the average value of the energy of a particle I would get? And I just calculate this here. It involves the probability that a particle is in 0 energy state, plus the probability that it's in the 1 energy state, the probability that it's in the 2 energy state, so on and so forth. And when I work this out, I get 1.25 epsilon. So on average, right, the average energy of the particle in this quantized set of energy levels is 1.25 times the energy level epsilon. And of course, right, that assumes that this total energy is 5 epsilon. If I change that constraint, right, then you have to redo all these calculations, and this number down here will change. But for the problem, as I've stated, that's the answer. It's kind of interesting to plot the probability of finding a particle with a particular energy versus the energy, right? So here's my 5 energy, it's actually 6 energy levels because I consider 0 as an energy level. So this is the 0 energy level. This is the first energy level, the second, the third, the fourth, and the fifth. These solid dots are the probabilities that I get from this chart here. And so you can check these probabilities by just doing the calculation yourself. If you plot those probabilities versus energy, you get a curve that looks like this. And surprisingly, if you want to try to fit the way this probability drops off, it can be fit very well with an exponential that depends on energy E. So if the energy E is equal to 0, 1 epsilon, 2 epsilon, 3 epsilon, 4 epsilon, 5 epsilon, right, you can get a curve like this that does a pretty good job of reproducing the probabilities that we've calculated for this particular system. This is the equivalent of the Maxwell-Boltzmann distribution for velocities in a classical gas, except now we're considering a system where the energy levels are quantized and the particles are distinguishable. This is the sort of curve that you get for that system. Why do you get this exponential fit? Why does that work so well? If you want a simple answer, the simple answer is if you calculate the probability that a classical gas atom has an energy E, it turns out that probability varies as e to the minus e over k Boltzmann T, right? So I derived this equation in the appendix of lecture 9.02 for ideal gas atoms, right? You can look at that if you're curious. I also have an appendix at the end of this lecture where I independently get this exponential factor out based on very general arguments. So if you're curious, you can look at that. But the bottom line is the probability varies with energy according to it varies exponentially with energy, right? For very general reasons, right? It's actually a universal law. So what we can say is, realizing that, we can say that if we have, let's say, 2 energy levels, E sub A and E sub B, we can ask what is the probability that you find a particle in either E sub A or E sub B. And based on this analysis that we just went through, right, we would say that the probability that you find a particle in energy E sub A is just e to the minus E sub A over k Boltzmann T. The probability that you find a particle in energy level E sub B is just e to the minus EB over k Boltzmann T, right? And that just comes directly from this discussion here, right? Or if you want a more general derivation, you have to see the appendix. This is the case for non-degenerate energy levels, right? If the energy levels are degenerate, then you have to include the degeneracy factor of each energy level, and you can say the probability varies exponentially with energy, and the pre-multiplicative factor here is just the degeneracy of each energy level. So this allows us to define something called the Boltzmann factor. The Boltzmann factor is just simply the ratio of the probabilities that you get particle in energy E sub B divided by the probability that you get in energy E sub A. The reason we take the ratio is because we don't know, these are proportionalities. There's numbers out in front. We don't know what those numbers are at this point in the course. So by taking the ratio, those prefactors cancel, and you end up with an expression that looks like this. If you're not interested in probabilities, if you're more interested in numbers, then you realize that the probabilities are related to the number of particles in energy level A divided by the total number of particles in the system, right? And so you can convert this equation into the ratio of the number of particles in energy B compared to the number of particles in energy A. That depends on the ratio of the degeneracies of each energy level, and it depends on exponentially on the difference in energy between E sub B and E sub A. And the important feature here is the temperature T, right? If you know the temperature T of the system and you know the energy difference between the two levels of interest, then you basically know everything over here, and that allows you to predict the ratio of the particles in each of those energy states. So if you understand that, then you'll probably understand this example, right? And to just illustrate the case, I go back to our two-dimensional infinite square well, the energy states that are appropriate for that. This was a problem that we discussed in lecture 5.01, so maybe you have to go back and review it. The important features are, these are the energy states that we derived when we quantized the wave function inside of this two-dimensional infinitely high quantum well, right? And these are the quantum numbers that specify each particular energy state. And you can see that some of these energy states are singly degenerate because there's only one set of quantum numbers that generates that energy level, while other sets of quantum numbers generate two energy levels with the same energy, which means these guys are doubly degenerate. And so I just asked the simple question, right? What's the ratio of the number of particles in, let's say, energy level 8, E0, compared to the number of particles that are in energy 13, E0, right? 13 E0's got degeneracy of 2, 8 E0's got a degeneracy of 1. And so to calculate the ratio of the number of particles in these two energy levels, I have to go back to this Boltzmann factor that we discussed in the previous slide. I write the important equation here, right? And I just to make the argument simple, I say 15 particles are found in 8 E0. How many particles are going to be found in 13 E0? So that allows me to define a lot of the parameters in this equation, right? I'm interested in calculating n sub b, the number of particles in the 13 E0 energy level. I have to specify what KT is, and so to do that, I consider three cases. I let KT equal to 1 E0, I let KT equal to 2 E0, and I let KT equal to 5 E0. So I just consider different temperatures to show you how the answer depends on temperature, right? And so if you look at the length of these arrows specify what KT is with respect to these energy levels. So this value of KT corresponds to an energy of E0 on this plot. This value of KT, right, corresponds to a unit of energy of 2 E0 on this plot. And then this value of KT corresponds to an energy of 5 E0 on this plot. And so I just evaluate this formula using these different values of KT, in this particular formula, or in this table, right? So everything is summarized in this table. The number of particles is always the same in the energy level A. That's by design. That's kind of a construct that we've imposed. And depending on what KT is, you can see that the number of particles that you would find in the 13 E0 energy level depends significantly on KT, right? If KT is very small, there's very few. There's 0.2 of a particle on average that would be observed in that energy level. If KT is large, then you can actually find 10 or actually 11 particles. If KT is equal to 5 E0, on average, there would be 11 particles in that energy level, 13 E0. So that's an example of how to use this Boltzmann factor equation. It's really an important concept that permeates, again, all science and engineering. You constantly see this, the ratio of numbers in different energy levels. You constantly see that as proportional to the exponential raised to the energy difference divided by KT. And so I hope this discussion provides you with some understanding of how that formula comes about. And I hope this discussion on this slide gives you some understanding of how to apply that formula to a specific case. So I'm a little bit over time. I got to quit right now. I'll just say that the next lecture coming up, we're going to actually discuss the number of available states. Right? This is a topic that we've discussed tangentially 2 or 3 times in this course, but next lecture we'll go after it with a little bit more intensity and try to clarify any misconceptions that you might have about that important concept. So we'll see you for that lecture whenever you get a chance to look at it.